Yeah. Let's wait 2 more minutes and we start. Today's lecture is quite easy, so it's not going to be a big problem, I hope. So I guess let's start then, and for the others, they will just have to watch the lecture at home, right? Hopla.
Yolo start.
So small question, do you guys have any questions about object detection in general, or about, what we have seen last time, Detectron, faster RCNN, all of these?
Yes. So what do you think? I mean, yeah, all of these algorithms are, they need some experiment and they have their own advantages and disadvantages, right? So, but
Yes.
in general, what do you think from your own expertise and your own experience, which algorithm does better in some particular, let's say, situations, and which one would you advise in situations where we have not many data, for example? Yeah, just with that few sentences.
For small data sets, I usually use Yolo v4 Tiny. It's usually the simplest and it's quite effective. But the new Yolo v8 is promising, so I would use either that or the Yolo v8 Tiny too.
Okay, and what do you think if we want to investigate what is happening? I mean, why do we have such a lower, let's say, accuracy, or we are doing good during the training and test phase, but in our validation uh, phase, performance is kind of poor. What do you think? What would be the debugging options for ML and these algorithms?
This sounds like a typical overfitting issue, right? So you solve it by solving the overfitting issue. Most obvious solution would be to add more data, but I'm guessing in your situation, you can't add more data, so you have to overfit. And in order to do that, you could do either like early stopping, or you could just not train the whole neural network, but only like the final few layers of the architecture. There are so many things that you could do actually, but the most important thing would be to get more data, right?
Okay, thank you.
Thank you. So before we go into the lab officially, and many of you asked like last time why we don't have any lab material for this lab and the one before it. And mainly because I don't want to give you any code that you can use for your projects or your assignments. What you should be doing is going online and using any code over there, right? So the goal is to help you guys find good resources that you can use to train your models and you can use to do the assignment, do the projects, and hopefully when you get a job, you can use to just fulfill your tasks at that job. So one of the simplest places that you could train object detection models on is this RoboFlow models list. Here you will see a long list of different object detection / segmentation models. So this gives you like two main sources. The first source is Detectron 2 specifically. Let's bring it up. Detectron 2. So here's Detectron 2, and as we said, it contains a long list of projects. So this is some of the extra projects that they're doing, but the main important part is, of course, the faster RCNN architecture and the mass RCNN architecture, which are both for object detection and then for instance segmentation. And then, of course, you could do any of these tasks extremely simply using their code. And if you're not looking for that realm of, the RCNN family realm, then the Yolo realm of families or of object detection models is what you're looking for. And the best place that you could find is this. RoboFlow is a very good start. The RoboFlow architecture is pretty exactly the same. So here, if you go, you should probably see that there is always a video. Here's the video. For each model, they have a very beautiful video explaining the code, how to train it. They give you some code on GitHub. They give you some like video guide, as I said, a tutorial that you can follow through. And most importantly, they give you a Colab notebook that you could easily use and train the model. So for simplicity, I'm gonna go with the latest. So it's Yolo V8, and we're going to train it. But you could do the exact same things on here with very few modifications. So maybe we could use, vision transformers and Yolo V4. So these look like cool. Yeah, vision transformers / Yolo V4. Where is vision transformers? We lost it. Somewhere it was here somewhere. Yeah, here's vision transformers. So vision transformers are they leverage powerful neural network models that apply. Okay, let's see it. Yeah, seems good. Not bad. The thing with vision transformers is that they're very heavy, like very big models. So you're not going to be able to train them fast on Colab. But let's start with Yolo V8. So Yolo V8, I think I already got it. Here it is. Yep. So this is the code for Yolo V8. I went ahead and ran it before the lecture. And wow, it already finished. So you can see that it's quite fast. Let's see if it works well. Okay, so it didn't give us this one. Okay, it worked. How about this? This was on train 6. Train 6. Okay, confusion matrix looks nice, I think. And all good. This is also train 6. Train 6. It's quite nice. Yeah. So this is the code that I just got from the this link over here, the Yolo V8. You just go Colab notebook and it gives you this link directly. You just copy it to your own, what is it called? To your own drive, and it will give you this beautiful code. No need to read anything, just directly first verify that you're using, what is it called? You're using NVIDIA, like you're using a GPU basically. And second step would be to install directly this Ultra Linux, which is very famous company in the field of computer vision. And yeah, introducing YOLO v8. They created YOLO v8 and they created YOLO v5 also. They're not that theoretically different from the rest, but they're much, much easier to train than, say, YOLO v4 or YOLO v3. Import it. Here we will try to run it and test it. So first thing you will see is that it's very minimalist, right? So unlike the code with Detectron, where we had long code to just test the model directly with that big config file and etc. Now everything starts here in one command. You can run it directly. So here, for example, you just call YOLO, and YOLO, here is YOLO. Where's YOLO? Yeah, so you just call YOLO since you installed it and just give it what task. There are three main tasks that you could give, which is detect, classify, and segment, because they have, you know, different versions that you could use. So there are some image classification models, there are segmentation models, and then there are some object detection models. For us, we're trying to go for the detection part. You can do either training, predicting, validating, or you can export the results. Here for now, we're just going to try the model. So we're going to predict using the predict function. And then, of course, the model itself. Here we're using YOLO v8n. There are other versions of YOLO v8. We could probably check. No, we can't check them. Let's go here and yep. So here they should tell us a list of the different versions of YOLO v8. No. Yeah, so there's the YOLO v8n, S, M, this is L, and then there's the X. They all have the same input size for the image, but overall, their performance is quite different. So for example, you can see that this one has a speed that is much, the number of parameters in millions is much smaller, the speed is much better or faster, I would say. And the accuracy, though, is much worse. So you can see here that the mean average precision for the validation data set is way worse than this one. And then, of course, the speed is much faster than this one. So the bigger you get, the worse the results might get. But for going back to the question of Siraj, this is the kind of networks that you would like to use, right? So this nano network. Then there's the small one. You shouldn't go to like the medium, large, or extra large models, right? So these models are very difficult to train. They take so much time and they take so many resources and they require a lot of images. But a nano model, I think, would give you very good performances for your task. All of these models are already pre-trained. So let's yeah, so all of these models are already pre-trained, and the good thing is you don't have to like know the link to where to download it or anything like that. Most cases, the code itself knows the locations and it will download the pre-trained weights for you. Unlike, for example, if you're working with YOLO v4, where you have to manually find the location where the pre-trained weights are saved in, and then you add it. But for YOLO v8, it's much simpler, as we said, because it's done with this Ultra Linux company, which is like a software company, so you can trust their quality, right? Save equals true, useless. The source is basically which image you would like to use. Source is quite flexible, so you could use, for example, a link. You could use an image that you have saved. You could use, I don't know, a folder. It's up to you. This conf is the confidence threshold, and it's basically here we're setting it to 25%. Which actually depends a lot on what type of model you're using. So usually larger models are more sure of their results. So speaking, for example, of X, for example, you shouldn't use 25 as a 25% as a confidence threshold. You should use something a bit higher. But the smaller models are usually not as sure about their results. So you can see in here, for example, this dog was predicted with a 29% probability, although it's correct. It was very, very under sure about its predictions. Whereas if you use some, I don't know, let's try and use the Yolo VX, for example. It's gonna take some time, huh? So as we said, it knows the location of the model where it is, and it just downloads it directly. And most likely it's gonna detect it in a different place, I think. Yeah, predict to, it's gonna predict it in predict 3, maybe. Yeah, so it's gonna take some time. But that's not a problem since we have the code running, so that's good. So here you can already see the size of this model is 131. So it's kind of a respectable size, right? So there are other sizes which are way bigger, but this is not bad, right? It's not gigantic and it's not super small. This is the previous results of the nano architecture. Let's look at this one. So you see, first thing you notice is that this bigger model is much more certain about its results, right? So if we put them hand by like next to each other, and we compare basically what was happening. So yeah, we can clearly see that the big model is more certain about its results, unlike the smaller model. And the big model was able to detect, for example, the backpack and other things. I will try to use the small model again, but with an even lower, right? With a lower confidence threshold. And let's see what happens. It should be fast, I hope. 1, 2, 3, 4. Okay, it was done. Let's see what happens. So yeah, so here we can see that this even the smaller model was able to detect the backpack, but since the smaller model was not very well performant, it predicted it twice and with a very, very low confidence threshold that even with like 25, we were not detecting this backpack. So it's up to you to decide basically which confidence threshold to use. And again, that depends on how much data did you have during the training, and of course, the size of the model. Something to keep in mind, big models are very certain about their results and they give good results in general. And smaller models are not very certain about their results. So if you would like to get good accuracy or good recall, you should use a smaller confidence threshold. But that's mainly it, right? If you would like to use, this is their, what is it called? Their command line interface. Very simple. Now, if you would like to include it in a, what is it called? In a Python library or somewhere, for example, you have like a, I don't know, a Python API that does the predictions and etc. You could easily call their YOLO function model.predict. Again, there is model.train, model.everything in here. So the Python SDK is very simple to use, very minimalist. So you really wouldn't have to think about the machine learning code that much. What you should be thinking about is basically your task or the task that you will be performing on that code, right? So here we can see it's very similar. You just create the model using the weights. Here we're using the nano weights, which are the smallest. And then, of course, you will have a results variable where you can just play with it, get the locations, get the confidences, get the classifications, get the names of the objects, get everything, right? So this was a simple use case or way to use the, what is it called, YOLO V8. Now, before we go deeper, we should start speaking about this RoboFlow. So RoboFlow is a very cool company also that provides annotations for models. So it allows you to annotate basically your own images. And this is something that you will be using in your homework. Yeah, so here's the homework. Now the homework assignment is on Moodle. So what is required from you guys is to basically take a couple of photos from your own environment of at least 2 objects, annotate them using RoboFlow. So upload them to RoboFlow and annotate them manually. It's super fast because, as you probably imagine, all you need to do is put a box on an object. So it's just you press and press, and that's it. So it's just 2 points, move, 2 points, move. So the annotation process should be very fast for you, but it's very important for like a computer vision engineer or like a data scientist to understand how to annotate, because most likely during your job, you're not going to be doing the annotations, but you're going to be like surveilling a lot of people who will do the annotations, and they're going to do a lot of mistakes. So you need to know how to fix those mistakes. First, train a faster RCNN model using Detectron2. Train either Yolo v4, 5, 6, or 7, only one of them, or 8, depending on what you choose, right? And only train the smallest size that you want. So either the nano or the small. And then, of course, evaluate both of these models based on their mean average precision, speed, and size. So coming back, the size is easy to use or easy to detect. Usually when it's downloading, it will tell you what is the size of that object. Now, going back to RoboFlow, what you should be doing is following these steps, basically creating a website, going to their interface, uploading a couple of images, and annotating them manually. Should be quite simple. Of course, you're not going to be uploading images with 100 objects. That's going to take some time. But if you're going to be uploading like a simple image from Innopolis with a couple of stop signals or a couple of cars or whatever you want to, or maybe if you go to the canteen and you take pictures of the dishes or of the chairs at your room, anything you want, it should be quite fast as a process. And as we have seen already, exporting the data set is quite simple. So from my side, I have a couple of data sets here. And the data set that we're going to be using is this balloon data set. This is not something that I annotated. It's exactly the data set that was used by, what are they called? The example on the Detectron example, the one that we used faster RCNN for. So this is the data set. You can simply upload extra images here, assign them for annotators. This is not what we're going to do. And then annotate. Here we can clearly see that everything has been annotated, but if there isn't any, if there was some image that is not annotated, you can easily just go through it and annotate very fastly. Once you finish, you generate a new version, and then you export according to whatever you want, and that will give you the code to basically run this script. So once you finish that, you should come here and paste the code that you get from this, right? So I said Yolo v8, for example, show code, and here it gives you the code that you just immediately copy paste to this place. It downloads the data set, so we can come here and see that the data set has been downloaded, right? Oh, sorry. Content, can you see content? Here's content, yep. Datasets, balloon one, and here's the dataset. So we see this dataset.yaml file contains the train validation data locations and some like metadata about the dataset. Number of concepts or number of classes, yeah, number of classes is equal to 1. And then of course the names of these classes for us is just one object. You can just rename it and say balloon, right? So now the file is like this. And once that is done, so once you download the data, again, very similarly to how we trained how we used the detection part, so YOLO task detect. Now we're going to do YOLO task detect, but the mode will not be predict, the mode will be train. Model is up to you. So I use the small version here. You could choose the nano version, which will be even faster. How many epochs do you want to use? Like, for example, do you want to train it for like one epoch over the dataset, 2,500, as you wish. So it depends again on the size of the model. So larger models require more epochs and smaller models require less epochs. And if you don't have enough data, then of course, you're not going to go a lot of epochs just to overfit the model. Image size is 800 or 600 as you choose. So this is just for like the first layer. Plots and pre-trained, let's say pre-trained equals to true. And then let's train YOLO V. And let's see, 600. Let's see how it goes. So first thing it does is it will give you the couple of information about the environment. It will tell you that it's doing the detection, training. This is the hyperparameters that you have sent them. So save equals to true, cache equals to false, device, we didn't set it, so it will take all the devices. Number of workers by default is 8. The project is not named, none. So a lot of information here. The optimizer is stochastic gradient descent, which is something that you probably have taken with Professor Khan, but there are hundreds of other optimizers that you could play with. Maybe something else might work for the data set from Siraj. And then there are some data, like what are they called? Some information about the, what are they called? Hyperparameters such as like mosaic, augmentation, and dropout. You can play around however you want with it. Intersection over union thresholds, right? So it's up to you. Coming here, number of overriding, for example, the model.yaml from number of channels is number of classes equals to 80. This was what was used to pre-train the model. But now we're just going to train it with number of classes is set to 1. All of these layers have been taken from the, what is it called? Pre-trained weights, but a couple of layers were not. Again, very similarly to what we have seen previously in faster RCNN. If we look a little bit closer, it should be telling us things with parameter groups. No. Scanning. So how many images do we have for the training? Are there some corrupt images? There are none. Albumentations is the data set or the library that they used to create the image augmentations. And the good thing about this one is that they have a cool demo online that you could easily use to test all the augmentations that they have. So let's, for example, play with Gaussian blur, right? So you see, it blurs the image even higher. And this allows you to play with the hyperparameters so you know what you're feeding into your model, right? Medium blur, no. Let's see, pixel dropout. Let's go. So this is something that you could play around with. Maybe this is useful for, again, Siraj example, because the more augmentation that you use, the better hopefully your model will be, or the less overfitted your model will be. So feel free to play with this. As you said, it's a very simple library that provides a lot of image augmentation techniques. Ooh, there is a professional. Yeah, so up to you, right? And also it gives you the code, the Python code that you can use to apply the exact thing that you have selected here. So it's quite flexible. And this is, as we said, the augmentation technique that they're using. So blur is equal to something, medium blur, they're using to gray, flash, and to grid size. Just different techniques, right? Validation, it tells you that there has 13 images for validation, none of them are corrupt, and the code has already finished, right? So as you can see, the data set is small, the model is very small, so it was able to finish the training in a very small amount of time, in 0.03 hours. Let's see how much that is in minutes. Minutes. So in 2 minutes, right? So it's quite fast. In 2 minutes, you can easily train a new model from scratch. And all it takes for you, like to code, is just to tell it where the data set that you want is, select what model you want to use, and everything else is quite fast. In 2 minutes, you have your homework already finished. So this is a new training, right? So let's go to content, runs, detect, and we're train 7. Let's see how train 7 is doing. So this is background and balloon. So it's finding all the balloons, but sometimes it's missing a couple or like over finding stuff. Let's see them. So this is how the training is happening, right? So it shows you the classification loss, the bounding box regression loss, and then this DFL loss, and then it shows you the precision over time. So clearly we can see that we could potentially, so again, going back to the Siraj example, here, I think at epoch 10, we already have a very good model that we can stop. So in case where you have an overfitting model, there is definitely no need to continue doing the training after epoch 10. So you could experiment a little bit with, what is it called? With early stopping, right? So we clearly also see that here, this was a very big change for the model. Let's see a couple of examples, right? Brain 7. So we can see it's doing very well, right? Yep. So it didn't detect these. That's a shame, but it did detect all of these, right? So that's nice. It didn't detect this one, and it didn't detect these. Yeah, that's what we get when you use the smallest model possible. There are other images too. Let's check them out for the results. Okay, it's the same thing. Let me check. These are the labels. Let's check this one, for example. This is for the training. So we can clearly see that the training data is much better, has much better performance than the evaluation data. Now we're going for train 7. And then the best weights, etc. Everything is good. Let's run. And this gives us a MAPE of, it's arriving. Yep. So it gives us a MAPE of 59%. If you would like to understand whether your MAPE is good or not, what you can do is come here and compare it against data sets that are very big, and this is the performance that we get, right? So this is the MAPE from 50 to 95 with like very big models. They're already performing 53.9 MAPE. So for us to have a MAPE of 59.8, that is beyond perfection, right? So this teeny tiny model trained on this small data set is doing very, very well, only because, of course, we used a pre-trained model, and that allowed us to use or leverage this transfer learning abilities and get these good results. But these results are actually very, very, very impressive for a model that was trained in 2 minutes, right? So again, we check here. We do some inference. Balloon 1 tests, we don't have it. Oh yeah, we don't have any test data set. So let's call it valid. How could we do that? So this is how you just do the evaluation. And this is how you do the detection on a, as I said, a large set of images, like a group of images. But for some reason it doesn't find them. Let me check why. Valid images, and here they are. No such files. Runs. Oh, okay. Yeah, it's this. So it's train 7. Yep. Let's run. Let's see. It loaded the images, and as you can see, it was extremely fast, right? So it did the inference on 11 images on 13 images in, I don't know, speed is 0.5 millisecond pre-process. The inference was 11.3 milliseconds, right? And 1.3 milliseconds post-processing per image at shape. So this gives us a total of like 12 milliseconds for one image, which is crazy fast, right? And for the predict, it should be also again predict 5. Let's bring predict 5 here. Yeah, so here are a couple of images. Works pretty well, right? Now, if you'd like to deploy it on RoboFlow, this is completely optional, but this is something that you will never actually do in real life. But for a real project, what you will be doing is you will take the trained weights. So you go to train 7 and weights, you will take this best .pt and you will use it as the weight for your model. Of course, you will create some, what is it called? RESTful API, or you will create some sort of server that allows to receive these images and then train on them, or then do inference on them. And the inference, as we said, is going to be as simple as this, right? So everything else, this, you can put these 2 lines of code anywhere and you want. So it's not really something that is very tedious to use or something like that. So it's very simple and very flexible. So that's it for YOLO V8. It's, as we said, it's not that big. It's not that simple. It's not that complicated to train any YOLO model on any data set you want, as long as you're using RoboFlow. RoboFlow is quite good. And the only reason it's actually quite good is because it allows you to export in many, many different formats. So as you can see in here, for example, if you want to train on, what is it called? On faster RCNN using Detectron, you can just export it as a COCO dataset. If you would like to train it YOLO v4 using the darknet architecture or the darknet framework, so you can use YOLO darknet. If you want to train YOLO v3, which is super old in Keras, you can just export its corresponding, weights or corresponding data set structure. If you want to train it in PyTorch, scaled YOLO v4, YOLO v5, YOLO v6, v7, v8, anything you want, it's done in here. If you want to take it to TensorFlow, to Keras, this is also again for Keras. Open API, so anything you want, you can easily do it, which is great, right? You can even do it for AWS services, right? So if you want to do it for AWS recognition custom labels, that's pretty cool. It's actually very nice. So as we said, it's very easy, very simple. And I think this homework is going to be something that you should be able to do in like half an hour if you have already taken the images for the data, right? So if you take the images for the data, it should be something that you do like in half an hour. Preferably don't take, for example, pictures of people or something like that. Try to take pictures of objects, right? So objects that will not complain if you take pictures of them, right? So do you have any questions so far about how to use RoboFlow or how to train any of these YOLO VX models? Quite simple, huh?
Yes.
Nice. So how much time do we still have?
50 minutes, I think.
15 or 50?
50.
Ah, so that's good. So let's take a 5 minutes break and then we come back, and what we will be doing is we will be going deeper into the concept of what is accuracy, what is precision, and what is recall. And once we have those, we will go into the concept of mean average precision, what it is, how to calculate it, and why is it the metric that is being used to evaluate object detection models, right? So see you guys in 5 minutes.
Okay.
So we are back. Let me just send you guys this link so that you and your friends can find it later. And let's go. So I'm guessing you already are familiar with the concept of accuracy, the concept of precision and recall, but just for the sake of, repeating these concepts, just to make sure that everybody is extremely familiar with these concepts, we'll go through it like very, very quickly and we will discuss it, okay? Once this is done, we will go through this, the mean average precision process, and we will discuss that, and then we will discuss a little bit on your project, because the start of the project ideas is this week, so we'll discuss a little bit about that, and we could end early if we finish early, and if we don't, then we'll finish on time, right? So what will be covered during this quick intro is confusion matrix for binary classification, confusion matrix for multi-class classification, calculating the confusion matrix with sklearn. I'm sure you guys already know how to do this. They will explain a little bit what is accuracy, what is precision, and what is recall, how to calculate each individual one, and what is the difference between precision and recall. And let's go. So the confusion matrix for binary classification is just the classification where you have either that object or another, or that object or nothing else, right? Or background. So this is the case where binary classification is, right? Positive and negative. So in order to do that, usually what you should do is, what you are using is some sort of like a thresholded class, or thresholded, what are they called? Prediction scores. So for example, 0.2 is smaller than our supposed threshold of 0.5. Then this 0.2 is predicted as a negative. 0.6 is bigger than our threshold of 0.5, hence it is predicted as a positive, so on and so forth. So here, for example, we go and we see the different predictions. The ground truth label is, of course, our label, what we already had, so positive, negative, etc. And then the predicted are, again, just depending on our comparison with our threshold. So the default threshold is 0.5, but as we have seen here, for example, you can set the threshold to anything you want. So for example, here we set the threshold to 0.1. So the threshold is up to you, right? Threshold by default is 0.5, but it's up to you to select any threshold number that you want. And this is how to build the first confusion matrix that we have. So this is the true positives and true negatives. This is something that we want to increase, the true positives and true negatives. And we would like to decrease the false positives and false negatives. First of all, how do you read this true positive and true negative, right? How do you read them? So these words are like comprised of two parts. Let me try something. I want to try a new thing. Not sure if it will work, but let's see. It's going to take me some time to set it up, but if it does work, it will make the lecture much more flexible. Displays. Okay. And done. Let's see if we can do it. Okay. Now let me share the screen. Can you guys see the screen?
Yes, we can.
Okay. And this works?
Yeah.
Wow, that's amazing. That's really, really cool. Okay, let me just bring this a bit closer. Yeah, I'll be using this technique hopefully in the future. So how to read this word true positive and true negative? Split it into two concepts. The first concept is whether there is an accuracy. So the accuracy is the first concept. The second concept that we're having, or we have to predict, is the predicted class. Sorry, predicted class. So when I say something like true, negative, that means that the prediction that I made is correct. So it's a true prediction. It's a true, it's a correct prediction. And when I say something like positive, it means that I made a positive prediction. So I chose the class 1 as a prediction. So the second word has nothing to do with the actual class of that object. It's just a representation of what I predicted. So it's just something that I have predicted. Let me bring this here again and see if it works. Okay, works well. I can't do it. Yeah, anyway, we delete that. Super cool. So if I say, for example, something like false negative, what does that mean? Can somebody tell me what false negative means? Don't look at this. Just tell me from this, what does it mean? False negative.
Well, false means that you are incorrect, and negative is your prediction about the class.
Good. So if I predicted negative and my prediction is incorrect, so what is the correct prediction?
It is positive.
Perfect. Thank you. So I know this is a little bit confusing, especially when you go to a job interview and you're a bit stressed. So the concept of, what is it called? Of false positives and true negatives and etc. can be quite a tedious concept to look at. Let's go. Yep. So now I hope this helps clarify a little bit some of that doubt, especially during the times of not knowing what's happening. Okay, perfect. So this is just an explanation of exactly that. All good. Now, confusion matrices for multi-class classification are pretty similar, but now we're no longer speaking in terms of positive and negative. We're speaking in terms of red, black, red, white, so multi-classes, right? Multiple classes. So we will extend this view to go through multiple classes, or we can extend it to be class specific. Okay, so they're just going with the class specific one. So the class specific one would show the problem is whether it's a black class or not, whether it's a white class or not, whether it's a red class or not. There is another version of this, which is a much bigger confusion matrix that tells you directly red, black, white in the same confusion matrix. But for the sake of simplicity, this is just a small trick onto how to convert basically a normal multi-class classification problem into a set of binary classification problems. Calculating the confusion matrix with sklearn, this is something that is pretty easy and pretty straightforward. So you just go to sklearn.metrics and you'll find a very long list of different metrics. And one of them is this confusion matrix, right, directly. And you just print it. There we go. Now we'll get to the main part of our work, right? So the accuracy is the simplest thing. Let's start with the accuracy. As you can see in here, the formula for accuracy is quite basic, right? So the formula for accuracy is the true positives plus the true negatives, meaning our correct, let me start the annotation. Okay, start. So meaning correct divided by total. So correct divided by total. The correct predictions are those predictions that start with true. And the total predictions are everything that starts with true and everything that starts with false. So this is the accuracy. It's a very simple metric, not that big, right? Not that difficult to understand. Let me try to bring this also here. Yeah, nice. Again, very simple to calculate. Or you could use it through a metric. Next step would be the precision, right? So the precision is a very simpler concept too. That says true positives divided by true positives and false positives. So can somebody tell me what these true positives and false positives have in common?
That we declare them as positive.
So yeah, so out of everything, so basically how to represent this, out of positive predicted objects, how many are actually positive? So this is the precision. So the precision is something that is dependent on the model itself, right? So it is something that we calculate only from the output of the model. So what does that mean, right? So when we say this is a precise model, it means when it tells you this is a positive class, you can trust it. So it doesn't really say, for example, let's say, I don't know, a good precise model would be like you're working in a stocks trading, right? So you're working in stocks trading. There are lots of different stocks. Some of them go up, some of them go down, some of them just stay stable. A precise model would not give you all the good models. So it would not tell you all the things that go up. It will miss a lot of those things that go up, a lot of the stocks that actually go up. But when it tells you that this stock is going to increase, when it tells you that this stock is going to get a lot of like more money going into it, I don't know how stocks markets work, but when it tells you that this stock is good, you can trust it. It's very precise. It doesn't tell you that so it doesn't tell you how many times that it finds a lot of like the good stocks. Only thing it tells you is if the model is confident about this stock being a positive stock, you should trust it. It's highly precise in its predictions. Meaning, again, if it makes a positive prediction, you should trust it. So this is what precision is. Precision is true positives. Okay, what is this? Let me just clear everything and let's start. Yeah. So precision is the true positives divided by the true positive and false positive. Again, it's a concept that is related to how much can you trust the positive predictions of this model. Now let's stop this and we go down. I don't know how to go down. Okay. Recall, on the other hand, is a different concept. So let's look at this. So again, it is the true positives, but now it's divided by true positives plus false negatives. Can somebody tell me what is the common thing between these?
They are true in real life, like it's the one class in reality.
They are actually positive. So this tells you how likely it is for the model to detect a positive class in general, right? So that's it. How likely it is for the model to detect a positive object. This is not related to that previous one, right? So you can have a model that is very precise, but it does not have good recall, right? So a model that is very precise, it means that once it tells you that this object is positive, it's guaranteed that it will be positive. High recall, it's not about that. So high recall just tells you among all of the positives that exist, how much was your model able to get? How much was your model able to recall? To remember just the difference between precision and recall, remember recall is similar to like remembering. So in a word in English, Recalling something from memory is like remembering something from memory. So a good recall is a model that remembers the positives, right? So imagine that your model is looking at the training data and it remembers where the positives are. So a high recall model would detect the majority of those positives. Whereas a precise model only tells you that this is a positive when it's extremely, extremely sure that it is actually a positive. So these two concepts are, kind of enemies, but they're something that we aim for at the same time, right? So we aim for high recall and we aim for high precision, but it depends on the situation. So as I said, for example, in the stock market, you don't want to detect all the positives out there, but you just want a model that is very precise. A model that when it tells you to invest in Tesla stocks, that money will increase, right? Your money will go up. That's the goal. You don't want to detect all the positives. You want to detect one that is 100% guaranteed to be a positive a prediction, right? So again, precision and recall are concepts that you would want to play around with. And sometimes, of course, your model might be precise. Sometimes you want your model to have high recall, and sometimes you want the model to have a good balance between the two. So again, the precision measures the model's trustiness, right? So how much can you trust it in classifying positive samples, whereas the recall measures how many positive samples were correctly classified by the model. So again, both of them, when they are very good, very high, that means the model is perfect. But in usual situations, when the precision goes up, recalls go down. Recall goes down, right? Precision versus recall, this is actually quite interesting paragraph. You could read it another time. But that's mainly it, right? So we have spoken a little bit about precision. We've spoken a little bit about recall. Now we will speak about mean average precision. And it's a combination of both, precision and recall. By the way, do you guys have any questions about accuracy, precision, or recall? So if I ask you, for example, what is the function of precision? Precision is equal to? Plus what?
False negatives.
Yes, plus those which were predicted as positive, right? So basically it's the true positives divided by what was predicted as positive. Can you tell me what was predicted as positive? So it's the true positive plus
False positive.
false positive. So it was predicted as positive, but falsely. This is the precision. Can somebody tell me what is the recall? Again, it is true positives divided by true positives plus
False negative.
false negative. Why is it false negative? Because we are dividing by what is actually negative. So what is actually positive in real life? How can you find it? So it's the true positive. It was predicted positive and it's actually positive. And what was predicted negative, but it's predicted falsely. So this combination gives you all the actual positives in your test data set. Nice. I don't think I can scroll with my hands. All right, scroll down. So now we will be speaking about these concepts. First, precision recall curve for classifications. Then to the concept of average precision, again, from this precision recall curve. And then we speak a little bit about intersection over union. We have already seen it, so it's going to be fast. And then we speak about mean average precision for object detection. So again, this is the true classes. These are the predicted scores. We have a threshold of 0.5. If it's bigger than the threshold, we say it's positive, or else we say it's negative. This is the predicted values. We create the confusion matrix, precision score, and recall score. So here's the confusion matrix. Here's the precision of the model. Here's the recall of the model. Again, it's 4 true positives divided by true positives plus 1, which is precision. What is it? What is the 1?
False positive.
Let me write it here. So precision is equal to correctly predicted as positive divided by all those predicted as positive. And recall is correctly predicted as positive divided by all those that are actually positive. Nice. So we'll leave them here just throughout the lab, right? Let's see. Yeah, works. So again, so this is 4 divided by 4 plus 1, which is the false positives, and recall, which is equal to 4 divided by 4 plus 2, which is the false negatives. You see this 3? Nobody cares about that 3. Precision and recall curve. A precision and recall curve is the following. So you can imagine that we are moving our threshold from 0.2 to 0.7, and we calculate a new precision and recall at each different threshold. So this threshold that we calculated was this precision and recall that we calculated are the precision and recall for threshold equal to 0.5. If we change the threshold, some objects might become true, others might become negative. So the precision and recall will change. And the precision recall curve is basically exactly that. By changing the thresholds, by changing these different thresholds, we get new predictions, and hence we get new precision and recalls. I'm not sure if you guys already taken this in the machine learning course, right? So this is the intersection over union related to the intersection over union, precision recall curves. Have you seen this before? Well,
Not sure.
Okay, well, if you haven't, we're looking at it right now. So as we said, you calculate the precision and recall at a specific threshold. If you want to calculate the precision and recall curve, then you will have to take a lot of different thresholds, and at each one of them, you calculate the precision and recall. And what do? You take that precision and recall, and you build a chart. So let's say at 0.5, you found this point. At 0.6, you found this point. At 0.7, you found, at 0.3, you found this point. And then you found this point. And then you found this point. This is the precision. This is the recall. And at every single threshold, you find a new coordinate. And you just keep on putting all of these coordinates like this until you finish all of your thresholds. Okay? It's definitely a lengthy process, so we're not going to be doing it by hand, but that's why computers exist, right? So here we said we will go through different thresholds. Let's go down. Precision recall curve, it's a very simple function, goes through the list of precisions and the list of recalls. For a threshold in the list of thresholds, you calculate the new precisions, you calculate the new predictions, you calculate the precision, you calculate the recall, you append them, and this gives you the recalls and precisions at each individual threshold. So here's the new list. So as we can see, this is the list of precisions. This is the list of recalls. What happens when we go from small thresholds to high thresholds? Precision goes up. What happens when we go from very small thresholds to high thresholds? Recall goes down. So as we said, they are kind of competing concepts, but our goal is to maximize both of them at the same time in general, right? So this tells us, or this gives us the following type of curve, right? So this is the precision recall curve. Again, if you use different if you have like a much larger test data set and your thresholds are much smaller, so instead of using a step of 0.05, you're using a step of 0.01 or something like that, you will have a much smoother curve, right? It's not going to be like this. It's going to be like this. So it's a curve. But that depends if you have a lot of data or not. So this is the curve. Intersection over union is one way of calculating how good the model is, right? So intersection over union tells you your model is good or not. Intersection, no, sorry. Area under the curve. Yeah, sorry. Why I can't type anymore. Sorry. Oh, wow. So I'm using the iPad. Disconnect. Let me reconnect again. 1 second. Nice. I think now it should be back to normal. And where is it? Yep, here it is. Let me share again. Nice. Can you guys see this screen?
Yeah.
Nice. Let me bring this back here. Okay. Nice. And it doesn't work. Or it does work. Yeah, it works. Okay, it works. So this is the precision recall curve. And as we said, we will be calculating something called area under the curve. Area under the curve is one way of evaluating the model. It's similar to something like, I don't know, F1 score or accuracy. So it's just a different way of evaluating how good a model is. A good model would have this kind of precision recall curve, like just perfect model. Everything is under this. Everything is under this beautiful curve, right? Let me just erase again, like this. And that's what a good model would look like. But no model is perfect. So usually you will have something like this. And when you calculate the area under the curve, it will be like 0.8. This is a very good model. If you calculate and it goes like 0.3 or 0.5 or something like that, so it's not a good model. Now, yeah, this is the F1 score. You can calculate the F1 score. Or you could calculate the area under the curve, or what you can do is calculate the concept called average precision. So now we're starting to get into the goal of this whole description, which is the average precision. So average precision is something else that you could also calculate from the previous, where is it? The previous chart. I don't know if we can go smaller. Let me try to. Okay, like this. Let me close everything. And let's close this too. Close this. We keep that open. Okay. Mhm. Okay. Okay, this looks good. This looks like nice. Let me just. I can. Okay. I'll just try to bring it a bit down like this and annotate again. Oh, nice. So the average precision score is a function that you could easily call over this this precision recall curve. And what it tells you is the sum over from k is equal to 0 to n minus 1 of recall at k minus recall at k plus 1 times the precision at k. So it's basically an average of precisions, a weighted average of precision, and the weight of these precisions is the difference or the consecutive difference of recalls. Consecutive difference of recalls. Area under the curve is much simpler than that. So area under the curve is basically this plus this plus this plus this plus this plus this plus that. So it's kind of well, how do we say this? So it's kind of the sum of the difference of recall times the, or let's do it like this, right? How do you calculate the, what is it called? The area under a function like this? Let me simplify it a little bit. So this is the function. How do you calculate the area under a function?
Just take integral from this interval.
Sorry.
Yeah, take an integral
Of?
from 0 until n of this function.
Of what?
So of this function, I don't know. Yeah, precision recall. Yeah.
What is, how do you calculate this again?
I mean, just take an integral.
But in the case of non-continuous functions, right? So in the case of discrete functions, integrals, they become?
Numerical integration. Like splitting in small segments and calculating them as rectangles.
Which is basically just a sum of smaller integrals, right?
Yep.
Yes. So this is what's going to be exactly happening in our case in the same manner. What's going to happen is, this is the precision at, I can't, okay, I can't type anymore. Yeah. Okay. It disconnected. Yeah, we're not going to be using the iPad. Let's go back. Reset. Yeah. No more using the iPad. It's not comfortable. So what happens is, you take precision at step 1 and then precision at step 2 in here, for example. The difference in these different recalls multiplied by what this is, which is the precision, gives you
The area of this rectangle.
the area of this rectangle, and then plus the sum. The difference between this recall and this recall multiplied by this precision. Well, it's not going to be a perfect one, but it will tell you this. Plus, you take the difference in these recalls from this and this, and it tells you this area. And again, the last one is like this, and it gives you this area. So as you can see, it's not perfect, right? Because it misses a couple of these places. But if you make the thresholds smaller, meaning the jump from one from this place to this place is not as big as we just did, you will get an approximation of the area under the curve. So this average precision is kind of an approximation of the area under the curve. And how do you calculate it? As we said, it's a very simple concept. It's just the weighted average of the precisions, right? So this is the precisions, average of them. How are we doing the average? Using a weight. This is the weight of the average. And the weights of that is just the difference between two consecutive recalls. Okay? And that gives you the average precision calculations. So here the math is quite simple, right? So this is something that you can easily do. And yeah, here it is. So what is it called? The implementation of it on Python is quite basic. It's quite direct. So it takes the precision recall curves directly, and it gives you the average precision recall, the average precision value, the AP. In this case, it didn't calculate it. Yeah, it doesn't show us the actual value, but here it calculates it pretty easily. What we could do is we take this code and run it on Colab. Sorry. So here's a new Colab. Let's run it. So the AP is 88.9. If we want, let's go check the accuracy. Sorry. To the confusion matrix. No, accuracy score is better. We print also the accuracy. Scores. Yes. So the accuracy is 81% and the average precision is 88.9%. So as we said, again, this is just another metric to evaluate whether a model is good or not. Let's go to sklearn.metrics and check. Compute the area under a curve. What it takes is true y and then the score y, right? Example and the probabilities, right? And the predicted scores. And this one, we call it area under the curve. The area under the curve is 80, whereas the average precision is 88. Not bad. Now, we finished the major math. What is remaining is all of this is basically, again, for classification. All of what we have seen so far is just for classification. How do we convert a object detection results into a classification model or into a classification result, right? So previously what we had here was, yeah, we had just positive, negative, and some numbers, like some prediction score, some coefficients. How do we convert a object detection result into exactly this, positive, negative, and some numbers? Using the intersection over union concept. So the intersection over union concept, we have already seen it a lot in our, what is it called, in our lectures, but this one would tell you the case. For case A, where is case A? I don't know, where's case A? So here, case A, the intersection over union is equal to 2. So there is only a 20% overlap between the two boxes. For case B, the intersection over union for the two boxes is 0.5, like this. And for case C, the coordinates of the two boxes are so close, and thus the number is 0.9. So this is the intersection over union. It's a very simple concept to calculate if you have, of course, the ground truth box and the prediction box. Using this, you can convert any problem into a classification problem. So the class of the intersection over union is positive if the intersection over union is above a threshold, and it is negative if the intersection over union is smaller than a certain threshold. So for example, this one, we have correctly predicted it. This one, we did not correctly predict it because the intersection over union is not that big. If the threshold changed to 0.6, yeah, so basically this is how to convert a simple, what is it called? Object detection problem into a classification problem. Once you have that, you calculate the mean average precision for object detection. So the mean average precision, as it says, so it's just an average precision or multiple average precisions, and then we take the mean of those multiple average precisions. So MAP is the sum or the mean over all the APs, such that the AP K is basically the AP of that class K. What does that mean? So it's the mean over all the APs for each individual class. Each class, we will calculate its average precision, and that would give us the average, the mean average precision. Let me just get, what should I get? Hold on. And let me check. Yep. So if we go down, a little bit down. Yeah, so this is the average precision. Area is equal to all, and the intersection over union is from 0.50 to 0.59 or 95. This is what we are calculating, or what we are using here. Sorry, somewhere. Yeah, here as the thresholds for the classification. So we come back here. These are our two different thresholds. If it's bigger than 0.95, it's in this range, then it is positive. If it's not, then it's not category, it's not being used. This is the intersection over union for 75 as a threshold. So as you can see, the number goes, the more we go up, the more this number goes down from 50 to 75. And of course, the small, medium, and large, the smaller the object, the harder it is to detect. So this is the mean average precision for these thresholds with the area is equal to minimum. Area is equal to minimum is just basically the size of the object. If I remember correctly, they have this definition of what is small and medium and large in code of medium and small thresholds for detectron. Yep. Where are they? By default, from 0 step size. No. Nope. Yes. Yeah, here they are. So this is the, what are they called? The ranges for a small object is from basically 0 to this number, and the ranges of medium objects is from this to this, and the ranges for a large object is from this to this. This is also something that you can configure. So this is part of the, what are they called? The hyperparameters of your model. You can easily change what is the definition of a medium object for you and what is the definition of a small object for you. But in general, the average precision goes up the bigger the object gets. Again, this is average recall. Average recall is not really used as a metric to evaluate, but it's basically the inverse of average precision. So it's the average of the recall weighted with the changes in precision, consecutive changes in precision. So this is the APL, so average precision large, average precision medium, average precision small, and this is the average precision 75, average precision 50, and this is the average precision total. These are the results, if I'm not mistaken, for segmentation. Let me just make sure. Can you see anything here that speaks about segmentation? Results for VBox. No, so this is the results for bounding box, the regression, and this is the results for the segmentation. Surprisingly, the results for the segmentation are better than the results for object detection, which is not something that I usually see, but that's good news. Okay. Okay, so here's, for example, it's good, but here it's not good. Well, that's weird, but that's okay. So this is what basically the average precision is, or mean average precision is. It's a calculation that goes through different thresholds and calculates basically the average precisions for each one of those different thresholds. So we go through different thresholds, we calculate this precision recall curves, we calculate the average precision from those different recall curves, and then using a intersection over union, we convert a object detection problem into a classification problem. And through that, we calculate the average precision. Once we have the average precision for each class, we calculate the mean average precision, which is basically a sum of, or like the average basically, or the mean of all the average precisions for different categories. So for this problem, it's not going to be very easy to do that since we have just one class. So the average precision is the mean average precision. But in the cases where we have multiple classes, we should get another table similar to this that says balloon, or that says, I don't know, animal 1, here's the average precision, animal 2, here's the average precision, animal 3, here's the average precision. And it tells you the mean average precision would be the average of all of those, weighted usually by the number of samples for each individual class. Does that explain a little bit what the concept of average precision is? How did we use a concept from classification in a problem of classification and why it's being used? I hope so. If not, then you guys could just quickly glance through this again, and if you want, you could just copy the code and see it by your eyes and see how it's done the calculations. I want to go back here and tell you guys that the what is it called? The deadline, or this assignment is due on 7th of March, which is in how many days? I think 14, almost less days, right?
It's actually, I will say 6th of March, since 12 a.m. is
No worries.
the midnight.
Yeah, we will push it, no worries, right? So basically 25th, the next week is the 4th, and you guys should give it on the 7th, which is, yeah, okay. So you have 1 week and almost a half to do it. If you will need some extra time, I will require to see the, what is it called, the progress. And if you guys just didn't finish in time, then I will give you 2 extra days to finish it. But if you haven't even started, then I will not really, of course, give you a postponement of for the assignment. So please start, take as many pictures as you can, build the code from the library that I sent you. So either from here, any one of these works well. And of course, from the faster RCNN using Detectron. Compare them both on mean average precision, speed of inference, and of course, the size. You can include other concepts like speed of training or anything you want. And yeah, the report should be on GitHub directly. So you just give me your GitHub link, GitHub repo link, and it should contain a very beautiful README that explains basically these 5 steps, especially the step of evaluation. And it should contain a link to a Colab that is working code. And of course, the code from Colab that is copied or downloaded directly from Colab and posted on GitHub, such that I can just read it on your own GitHub, right?
Okay, may I ask one question?
Yes, of course, go.
In the assignment, in the first part, it says like at least 100 instances between all objects. What does it mean?
So for example, if you have 2 objects, I don't know, mouse and something else and cat. So between all of them, you should have around like 100 objects. Do you think that's a lot?
I don't understand what does it mean. Like
This. So this is a data set of 74 images, right?
Okay.
This one image, it contains 3 of them.
Okay.
So when I count the number of objects that you have in all your images, it should be high. It should not be 3 or 4. It should be close to 100.
Okay.
At least 100 instances between all the objects.
Okay.
So that would be like, I don't know, 25 different pictures. And that's it. Make sense?
Yeah.
So if you guys have any, how much time do we still have?
No idea.
Yeah, it's a Sunday anyways, right? So thank you guys.
20 minutes, I think. Excuse me, could you please specify how many pictures do we need to take of how many objects? We need to choose one object type and make pictures by my own, and how many pictures I should take?
As you wish, as you wish. So for example, if you take a picture of, I don't know, the cars in the parking lot of Innopolis, in one picture, you will already have like 20 or 30 different cars. Okay?
Okay, and how many I need for this task? About 25 or 30?
Yeah, 25 or 30 different images is good.
Okay, thank you.
Thank you. Do you guys have any other questions?
No, thank you, Professor, for the lecture.